All right, so I'm going to go over the questions from the buffer review so you have an idea of some of the calculations you're required to do for acid base. So first thing, it says pH of a solution that contains 0.818 acetic acid. So that's going to be your weak acid, HA, the generic form of it. And sodium acetate, we know that's a heartbreaker, so we know it's a buffer solution. So whenever you calculate the pH of a buffer solution, you're going to use Hasselhoff. pH is equal to pKa plus the log of the acid over the salt. So to get this answer, you're going to go 0.818. And then what you're going to do is you're going to put 0.172 on the top because that's the conjugate base. When you pop all that in, what you're going to do is, let me see here, you're going to do this. So when I do the calculation, it's going to be 0.172 divided by 0.818. Boom. I'm going to take the log of that one, log that sucker, and then I'm going to add it to the pK, which is 4.74. And my total answer is going to be 4.06, which rounds close enough is going to be A. There's your setup for that. The next ones are the same. The reason why there's an error with this one is the error is it's supposed to be 1.77 times 10 to the negative fourth. It's the exact same idea though. What you're doing is you're just taking Hasselhoff. So you're just taking the value of sodium formate because it cancels. That's the ion. 0.23 is going to go on the top. 0.37 is going to go on the bottom. And then you basically do the exact same thing. So what you're going to do is you're going to go 0.23 divided by 0.37, boom, log it, and then you're going to add that, so negative 0.206, or basically 0.21, negative 0.21, to the pKa, and if you take 1.77 times 10, this is the difference, times 10 to the negative, right, and you take the negative log of that, I just messed that up. 1.77 E for negative. And then you take the log of that. It's going to be 375, so it's going to drop down. So it should be 3.55 when you pop it in there. So you just put the pKa right in there. Pop that in because the pK for this is 3.75. That number was just messed up, and the correct answer is C. Same thing with the next one. It's the same thing over and over and over. When you go to do the setup, it's going to be benzoic acid. What you're going to do is they tell you 0.25 moles. No, look, it's in 1 liter solution. So I put 0.25 moles on the top. Actually, no, that's the acid. I messed that up. So I'm going to put the acid on the bottom, which is 0.25. The 0.15 moles of sodium benzoate goes on the top. Same idea, you pump that all in there. So what I'm going to do is I'm going to go 0.15 divided by 0.25. Get that. I take the log of it. That's going to be, when I do that, I get negative 0.22. Then I just need the pKa. Well, the Ka is 6.50 to the negative fifth. If I take the log of that, negative log of that, I get 4.18. And then what I'm going to do is I'm going to add a negative 2.2 to 0.22 to that, and that's where I get the C, 3.97. Same idea, you're just using Hasselhoff over and over and over. Same thing basically with this. If you take a look, my pK is 4.18. If I take a look, I'm taking my moles of my acid is going to be 0.15. So then I'm just basically changing this. So on the bottom, it says 0.15 moles of benzoic acid, so I put 0.15 there, 0.30 of the conjugate base, and then you're going to basically calculate it out. Notice how the base is growing, the conjugate base is growing relative to the acid, means that your value is going to be higher than the original pKa, because if it was even, it would be equal to the pKa, meaning like if I took 0.30 over 0.30, they were equal amounts. That's what we call a perfect buffer solution. The log of 1 is 0, so pH is equal to pKa. So anytime you have a greater conjugate base, this value is going to be slightly higher than pKa, and you can see C is the correct answer for that one. Now, next one. If you take a look here, 5. Calculate the pH of a solution. That is a weak base, ammonia. So I'm going to put 0.750 there, 0.25 there. I'm going to go log, and then I'm going to go plus the pKb because it's a base, equals POH minus 14 is all I'm really doing. That's what I'm basically doing there, because it's the same idea. you're just going to, so my PKB is going to be 4.74. So then I pop it in my calculator, I go 0.250 divided by 0.750, Hasselhoff it, log it, I get negative 0.474. I'm going to add that to 4.74, and I get 4.26, but I have to subtract that from 14 because that's my POH, and I get 9.73. Same thing, exact same thing for this calculation as well. So you're setting it up, you have your KB for methylamine. So what I'm going to do is I need to calculate my KB. My base goes on the bottom, my conjugate acid goes on the top. So 4.4 E, 4 to the negative. I'm going to take the negative log of that. I'm going to get 3.36. So there's my PKB is 3.36. I just took 4.4 times 10 to the negative 4, took the negative log of it. My base is going to be solid methylamine. Actually, nope. Methylamine's right here, 1.1. So I'm going to go 1.10 moles of methylamine. I'm going to put 0.350 on the top. 0.350 divided by 1.1. Take the log of it. I get 2.49 plus 3.36. When I get that, and then I'm going to subtract that from 14, and my answer comes out to be something I don't have there. I must have made a mistake somewhere. 4.4 E, 4 negative, that, log, sign change. Oh, it's 2.36, it says. 2.36. Ay caramba. So this is 2.36. I don't know how I messed that up. Okay, so that's my PKB. So then I go 0.350 divided by 1.10 log, add it to 2.36. I get that. And then I'm going to subtract it from 14. And I still don't see my answer up there. I wonder what I'm doing wrong. 4.4 E, 4 negative. Boom, log. Oh, it's 3.35. I did have it right the first time. 3.35. I'm going 0.350 divided by 1.10 log. There we go. Negative point. So, okay, so when I did this, my log, I got negative 0.497. So I add that to 3.35. That gives me 2.85. Subtract that from 14, and I get 1114D. That was wicked. So the thing that you're doing here when you set this one up is you take the negative log of the PKB, which is 4.4 times 10 to the negative fourth. That's going to be 3.36. Then when I go to stack it up here, I'm going to take the 0.350. Because of the heartbreaker right there, the CL, that's going to cancel. Put the 1.10 on the bottom, pop it in and do the calculations, and I get a pH of 11.14. So anytime you have Hasselhoff, you're just popping in the acid in the conjugate base. In this case, it was basic, but it's the same idea. The idea of a buffer basically is trying to resist changes in pH. So A, keeps the pH of a solution constant or make it very, very little. What substances are present in a buffer? It's an acid and a base, and it's salt, which remember, salt just means it's going to be conjugate, so it would be its conjugate base or its conjugate acid, because that's what makes a buffer system. So a buffer system has to have a weak acid and a conjugate base, or you can have a weak base and its conjugate acid to resist changes in pH. 9, the addition of HF produces a what buffer solution to what? Well, if I'm HF, I need, and this is my weak acid, right? So this represents my weak acid. I need a conjugate base. My conjugate base would be taking H off. I meant with F minus. Well, the only thing that's going to give me F minus is going to be C, because if I put NaF in solution, what happens is I produce Na plus, which we know is a heartbreaker, and F minus, therefore giving me a buffer solution. Weak acid and a conjugate base or a negative ion. Next. 10. Which of the following could be added to a solution of sodium acetate to prepare a buffer? Okay, so sodium acetate is C2H3O2 and Na. But we know the Na is going to be a heartbreaker, so it's automatically going to delete. So I'm going to end up with C2H3O2 minus. So in order to make a buffer solution, definitely acetic acid, because I have a conjugate acid-base pair. So acetic acid automatically will do it. Okay, and then if I go and look, that's pretty much it. Sodium chloride, these are going to cancel out. Ammonium is a weak acid when you put in solution. The acetate ion's already there, and hydrochloric acid, we're not going to deal with. So for right now, for this point and purposes, we'll say the correct answer is A. 11. Which of the following could not be added to a solution of sodium acetate to prepare a buffer? Okay, so definitely hydrochloric acid, definitely nitric acid, right? So it says which could not be added, and then E, more than one of those answers would be correct. 12. Which of the following could be added to a solution of potassium fluoride to prepare a buffer? Well, KF. So what I'm looking at is KF. I know that's a heartbreaker, it leaves an F minus. So what I'm really looking at is I need the acid with it, and it's not present. It's not there. So yeah, that's going to be an issue. The thing there could do is that if you add a strong acid to a salt, we haven't gone over this, you could prep a little HF. As you add it would create somewhat of a buffer solution, but we really haven't covered that. So the correct answer for 12 would be C, but it's not anything that I'm really focused on. Let me see, I think that's it. I just did the first 12 questions. So we'll stop right there.